Ever feel like you're just drowning in information trying to figure out what actually matters?
Oh, definitely. It's overwhelming.
That's kind of why we do this deep dive, right? To cut through all that noise. Today, we're looking at something pretty fascinating in design, the huge impact of data.
Yeah, it's really interesting how design is moving, beyond just pure intuition now. We're seeing real-world info treated as data becoming this essential tool.
Absolutely. And to help us get a handle on it, we looked at this presentation from the buildSMART Conference 2024.
Right, the one shared on the Code for Design NJ channel on YouTube.
That's the one. And the presenter has this, well, really diverse background. Think architecture, but also software engineering, and a deep dive into computational design.
So they really speak both languages, building and computers. That's quite a mix.
Totally. And their experience, it spans from running an architectural practice, NJ Studio, since like 2004.
Which focuses on data, AI, computation, viz, all that stuff.
All the way to working remotely now for Radiant, that Silicon Valley startup, and they used to be at Esri.
The ArcGIS people.
Exactly. Plus, a research fellowship at MIT's Sensible City Lab. It's this blend of, real-world practice and deep academic thinking.
It's a serious background, gives them a pretty unique view on how data is connecting design and computation, which were often pretty separate worlds.
And the depth is kind of crazy. They have something like 1,300 videos online.
Wow.
And maybe 200 articles, all about computational design, plus lectures, a book. The book really pushes this idea that designers need to get coding and data today.
Yeah, the world's changing so fast that the presenter talks about needing a vessel, right? Some way to keep learning and building on these changes.
Which brings us right to the main point, I guess. How do we take stuff from the real world, tangible information, and make it digital?
This idea of discretizing spatial information, taking something continuous and breaking it into data points.
And then how do you translate design thinking, the actual process, into instructions a computer can follow?
That's the codification part, turning the design method into code.
Okay, let's unpack that a bit.
Yeah.
It sounds like we're hitting some basic computer science ideas here.
Definitely. We're talking data structures.
Which is like how best to arrange the design info in the computer's memory.
Exactly. And algorithms, the step-by-step way to process that data.
And the presenter actually says a designer's concept is basically an algorithm.
That's a really key idea. Think about it. A designer has a method, right?
Right.
A sequence of steps to get to a solution. If you define that clearly, boom, it's an algorithm.
And the things they work with, shapes, spaces, materials, need to become data the computer gets.
Precisely. Data within a structure it understands.
It's pretty wild how things like AlphaGo beating Lisa Tosidal, what was that, 2015?
Yeah, around then. And ChatGPT more recently in 2022.
How those events have sort of shifted, how designers see technology's potential. Now we're seeing tools spitting out floor plans, elevations.
Even whole 3D models. The speed of change is incredible.
It really is. And you look at things like BIM, smart cities, digital twins. They seem different, but the presenter says the common thread is
Data. It always comes back to data.
collecting it, processing it, finding insights, and then feeding that back into services or designs.
That's the core loop.
And here's where my mind was kind of blown. The presenter calls data a design material for the 21st century.
That's a powerful way to put it.
It draws this parallel to how stone, glass, concrete, steel, how those materials totally changed design history.
So data isn't just like information about the design, it's part of the substance of the design. Like choosing a specific wood for its green, you choose data for its properties.
It really makes you rethink things. We usually focus on tangible stuff, right? But in this digital age, information, structured as data, it could be just as fundamental.
Yeah, it's a big shift in perspective.
They even mentioned UI/UX designers in Silicon Valley who were designing virtual spaces.
Right. Makes you think maybe architects need to broaden their definition of materials too to include data.
Definitely an opportunity there. But the presenter also made a good point. Data itself isn't new.
Yeah. Like choosing the right stone back in the Stone Age. That involved evaluating data hardness, shape, usability.
But what's different now is our ability to process it, to refine it, like incredibly quickly and on a massive scale.
Totally. The sophistication is just leagues beyond.
And it's everywhere, isn't it? Geometry, buildings, cities, landscapes, how things look, material properties.
GIS, Geographic Information Systems, being a huge example.
So the main reason to use all this data in design is to build better decision-making processes.
Exactly. Where data is constantly generated, checked against criteria, transformed as the design develops.
Okay, so the presenter breaks this data down into two main types. Vector and raster. We probably know the basics, but let's go deeper. Vector isn't just points and lines.
No, not really. The presenter wants us to think of it more actively as a tool for, like, manipulating form, storing it, even applying forces.
Forces, like how?
Imagine vectors defining how much force you need to push or pull a point on a digital mesh to shape it. It gives you really precise control.
Okay, that makes sense. So collections of these vectors build up lines, meshes, those smooth NURBS curves you see.
Right, the building blocks for most digital forms we use. And it's this constant back and forth, tweaking the vector data, seeing the result, refining it.
An iterative loop. Got it. And then there's raster data.
The grid system. Each cell or pixel gets a value. Could be simple, like one for yes over for no.
But it can handle really complex stuff, even with that simple structure.
Think GIS again, that 10 by 10 meter square on a map. The color tells you something green means park, maybe? It breaks down the continuous real world into these discrete chunks.
And what's interesting there is the relationship between the pixels, right? The neighbors.
Exactly. That's core to how convolutional neural networks, CNNs, and AI work. They're great at spotting those spatial patterns in images, like understanding textures or shapes based on adjacent pixels.
And that's being used now for analyzing cities from photos and stuff.
Yeah, definitely.
The presenter had a cool example. Trying to find a spot on a map that meets several criteria.
Right, like find me a pixel that has X% green space nearby, is close to a subway, and has low crime.
That's a way to actually codify part of the design process, like site evaluation. You're turning requirements into a data query,
Precisely. And building on raster, you get voxels.
which are just 3D pixels, basically.
Pretty much. A 3D grid, useful semantically, you can store multiple layers of data in one voxel, and physically, which is obviously relevant for architecture. We'll see some project examples later, they said.
I like the analogy they use here. Designers are like chefs.
Ah, yeah, the ingredients analogy.
Data is the ingredients, and different chefs, different designers use the same ingredients, but create totally different dishes based on their own concepts, their experience.
Their recipes. It really highlights that the designer's intent, their algorithm, is still key, even with the same starting data.
Then they talked about graph data structures.
A more traditional way, maybe, nonlinear, showing relationships. Like in a BIM file, Revit was the example.
Where walls, columns, beams,
Yeah.
they aren't just separate things, they're connected in this graph.
And they have metadata attached, height, width, material, whatever. It's all linked.
And that interconnectedness is crucial for codifying design processes, letting you set up rules and dependencies.
Absolutely. It's how you can say, if this wall moves, update the connected beam.
And things like parametric design, generative design, rule-based systems, these are all ways of strategically using that data, primarily vector data, through code.
Yeah, they're like different high-level strategies for cooking with data.
So, just to wrap up this first bit, we capture real-world info, turn it into digital data structures, vectors, rasters, graphs.
And our design processes become algorithms that work on that data.
And connectivity, the relationships between the data points, is super important. That's the difference between, say, old CAD and modern BIM.
Yeah, CAD often being disconnected lines, BIM having inherent relationships. It's a big leap.
Okay, so we've got the data side. Now, what about the mindset, the perspective needed for computational design?
Right. The presenter defines it simply as integrating computer science tech into design. But the key is computational thinking.
Which is that problem-solving approach, breaking things down.
Decomposition, yeah. And abstraction, focusing on what matters, ignoring the noise.
Pattern recognition, finding similarities.
And finally, creating the algorithm, the step-by-step solution.
It's just a different way of thinking than we usually do, isn't it? That banana example was funny but spot on.
Uh-huh, yeah. Buy a banana seems simple to us. But for a computer, which banana, which store, how many, why, you need way more detail.
That level of granularity.
Exactly. And tied to that is the type of reasoning. Deductive versus inductive.
Deductive is deterministic, right? 3 times 3 always equals 9.
Always. While inductive is probabilistic, like Netflix recommending a movie based on what you watched before, it's a likely guess, not a certainty.
And machine learning leans heavily on that inductive side.
It does, which means it's not the right tool for every problem.
You wouldn't want your airplane flown entirely by an inductive system, right?
Probably not. For critical stuff, you need deterministic certainty. The choice of method really depends on the problem you're trying to solve.
The speaker even mentioned their own PhD work using machine learning and realizing how designers talk, often quite descriptively.
Yeah, needs translating into something a computer can actually work with. bridging intuition and logic.
It's a real challenge. And we saw that initial hype with tools like ChatGPT.
Followed by a bit of a reality check, maybe, a plateau, suggesting ML is great for certain tasks, but not a magic bullet for everything.
Sometimes traditional methods are just better suited.
Right. And the presenter's teaching approach reflects this thinking about whether you need the absolute best solution or if an optimal good enough one is actually more practical.
That's a very design-centric way of looking at it. Optimization versus satisfaction.
Because often in design, there isn't one perfect answer, but a whole range of good ones. Computational thinking helps explore that range systematically,
This all leads towards what they call design science.
explicitly using data and algorithms in design, like how other fields became computational X, computational linguistics, etc.
And the point isn't that we lack tools. There are tons of tools.
The real issue is understanding the computer science principles behind them and how to apply them smartly in design.
Okay, makes sense. So how does this play out in actual projects? They moved on to some examples.
Yeah, and importantly, computational design isn't always about like designing a whole skyscraper from code. It can be applied to smaller, meaningful parts even early on.
Like schematic design.
For sure.
Yep.
The first example was from MIT Media Lab back in 2015 with Kent Larson analyzing city information.
Accessibility, how far can you get in 5, 10, 15 minutes?
Right. They did it by pixelating the city, basically, mapping data like views, distance, slope onto a grid.
Creating this layered, holistic view for architects, not just isolated data points.
Then the Korean project on urban character, using third-place data.
Those spots outside home and work, cafes, parks, libraries, comparing LA, Boston.
And S's HQ location, using where these places are located to figure out what gives each city its unique vibe.
So using data modeling, inference, to compare them and see what kinds of spaces define their character. That's using data for something quite qualitative, almost.
It is. Then there was the comparison of Sulo 7017 and the High Line in New York.
Just after Sulo opened.
Yeah, 100 days in. They used semantic segmentation on images, basically, identifying and quantifying different elements in photos.
Like what percentage is greenery, paving, people?
Exactly. And analyzing keywords associated with photos online to gauge user perception, then comparing that to the original design goals.
That feels way more objective than just asking people what they think. You get actual data.
It provides a much more robust baseline for that kind of analysis. They also briefly mentioned using color data and work at Radiant training models for maps. Network analysis, too.
Okay, then the Singapore parking garage project. That sounds super practical.
Very. Optimizing parking layout in weirdly shaped plots.
Using a parametric approach.
Yeah, developing this algorithm based on rotating and fitting standard parking bay layouts. But the key thing wasn't just finding one best layout.
Right, they generated a range of top options.
Options based on maximizing spots, minimizing columns, letting the human designer make the final choice from a set of really good data-vetted possibilities.
That blend of computation and human judgment seems important.
Definitely. Then the column optimization for a roof. Using agent-based modeling. That sounded wild.
Yeah, these little agents representing different needs, like human agents wanting open space, structural agents needing support points.
And they sort of negotiate computationally to find good column placements. It's iterative, though.
Doesn't always work first time.
Nope. They said it often took multiple runs tweaking things, which sounds a lot like actual design, right? Trial and error.
For sure. And the Harvard GSD thesis using Jan's generative adversarial networks.
To generate 3D models from 2D slices or photos. Mind-blowing stuff.
Like teaching an AI to recognize cats, and then it draws new cats you've never seen. But for 3D models.
Pretty much. Learning the essential features and then creating novel variations based on that learned style or pattern.
Which leads straight into that big philosophical question. Is machine learning creative?
If it's fundamentally a generalization machine, as the presenter put it, does generalizing equal creativity?
It's a tough one. They suggested maybe creativity involves good errors.
Unexpected deviations from the learned patterns, but ones that still work or are even interesting, like picking a slightly quirky gift or that specific beer after basketball.
Socially agreed upon trends, but with acceptable variations.
Right. And the key is these models learn from data sets, so any biases or characteristics in that data
Like where the data for a language model was scraped from.
can influence the output, shape its worldview or biases.
So we need to understand where those good errors in AI design come from.
Yeah.
It's not magic. It's rooted in the data.
Absolutely.
Yeah.
Then landscape architecture, Seems like a natural fit for computational design.
Because there's so much environmental data readily available.
Exactly. Sunlight exposure, you can voxelize that, soil pH levels, slope, hardness. You can build really detailed data models of a site.
That AR tool sounded cool, placing virtual trees and seeing how they might grow based on the actual site data.
Yeah, integrating data visualization right into the workflow. Pretty neat.
And that game-like thing showing interconnected processes. Water affects trees, trees become timber, timber feeds a factory.
Highlighting how design decisions ripple through a system and how you can refine computational models to capture those links.
CFD, computational fluid dynamics, obviously well established already.
A classic example of computation being essential in design and engineering.
But the GSD project with the swelling material,
Yeah.
that was different.
Yeah, a material that expands in sunlight, contracts in shade. They had to computationally figure out how it behaved, how much, how fast.
And use that understanding to parameterize a responsive facade system,
Yeah.
controlling light based on the sun.
Exactly. Linking material properties directly to computational control.
I like the analogy they use there. A computer might only do addition at its core.
But through layers of abstraction, we get rockets and self-driving cars.
And similarly, new materials drive new tools, which change design possibilities and maybe even creativity itself.
It's a feedback loop.
The presenter also mentioned their huge collection of resources built up over 15 years.
And trying to share that knowledge through workshops, materials.
That list of 130, 140 FAQs from students sounds gold, just knowing the common sticking points.
For sure. And referencing a past lecture on graph data structures, again, emphasizing understand the fundamentals. AI isn't magic.
It depends entirely on the data it's trained on.
Right. Which relates to that anecdote about a design critique.
Where everyone was focused on how smart the AI seemed, instead of the designer's actual problem solving.
Yeah. The presenters stressed needing to ask what data was used, what model was chosen, how predictable are the results. Don't just be impressed by the output.
And the difference between normal programming, which should error out if wrong, and machine learning.
Which always gives an answer, even if it's a hallucination, totally nonsensical.
So foundational knowledge is key, rather than just chasing the newest shiny tool.
Well, absolutely. Which makes their current project sound fascinating. They time-coded all those videos and articles.
Meticulously, apparently. And now they're training a language model, like Llama, on their own material.
Wow, to create a specialized search engine for computational design info?
That's the goal.
Yeah.
A searching machine for their specific domain. That's ambitious.
Very. And that final anecdote from 2008.
About the crazy idea for a big touchscreen phone with multimedia and people scoffing.
And then, boom, the iPhone arrives, shows how fast things can shift, how radical ideas become reality.
So the two big takeaways from all this.
First, adapt your mindset. New wine in new bottles. Embrace the new tech. Don't just try to fit it into old ways of working.
And second, focus on the fundamentals. What won't change in the next 5-10 years?
Like the core ideas of data representation vectors, rasters, graphs, and data manipulation, those principles endure even as specific tools change.
Because if you understand those basics,
Adapting to new AI models or software becomes much easier because they're often just building on their same core concepts.
makes total sense. And for anyone listening who wants to go deeper,
There's that QR code in the source material linking to more resources. Definitely worth checking out.
yeah, this whole deep dive really hammered home how central data is becoming to design.
From the basics like vector and raster to codifying processes to the whole way of thinking computationally.
It gives you a solid framework, I think, for understanding and maybe starting to use these approaches.
And makes you think, how could this apply to my work, my area of interest?
Which leads to that final provocative thought.
Yeah.
If we really start thinking of data as a design material like wood or steel,
How does that reshape the future of buildings, cities, the whole profession? What new things become possible when information is a fundamental building block?
something to really chew on. So check out those resources, keep exploring, and think about that vessel you're building to navigate all these changes in design and tech.